So for the last 4 or 5 years now, the IEEE and then the IETF have been trying to propose open standard solutions to address the automation problem. And the generic name that we the envelope name that we used for that effort is deterministic networking. So the time-sensitive networking, TSN, at the IEEE is part of this deterministic networking attempt. And in the same fashion, the DetNet working group at the IETF is also trying to serve deterministic use cases. So the first question is, what do we mean by deterministic? And effectively, in each scientific field, or even in philosophy, there is a definition for determinism. And basically, if you look at those definitions, and I have 2 of them in my screen here, we are mostly looking at eliminating the statistical effects in a system so as to be able to guarantee that the system will function over and over and over in the same fashion. So we can predict the way the system will operate in the future, which will be exactly the same as today, right? You can design a system, and that system will operate whatever the environments will operate in the exact same fashion. So basically for us, it means I know my flows, I know exactly what I'm injecting in that system, and if I can know that, if I have the causality, then I can know exactly what's going to happen to this flow in my network. So I control when I inject a packet. And if I inject the packet at the time I expect, with the amount of packets I expect, like every period, I know that this packet will be processed in the exact same way every time, guaranteed in my network, meaning that the loss will be under a maximum bound, and the delivery time will also be bounded. That's really what we mean by deterministic in deterministic networking. Bounded loss, bounded latency. And to explain better how determinism, quote unquote, can be introduced in a traditional network, I have 2 or 3 analogies that I really like. The first analogy is the analogy of a bus system. So I guess we've all taken buses in a city, and so we're used to the way they operate. There will be, say, a bus which will pass every 15 minutes next to your home, and that will take you next to your office. So if you know that the bus passes every 15 minutes, and you know that it takes, say, 30 minutes for the bus to go from your home to your close to your office, then you know that your overall time for transportation will be bounded by 45 minutes. Like, you can arrive at any time, you leave your home at any time, arrive at the station, you know that in less than 15 minutes the bus will be there, and in less than 30 minutes the bus will take you to your office. How can the bus guarantee those 30 minutes? Well, they can do that because they have reserved lanes in which there won't be contention with other traffic. You're used to seeing these bus lanes, and then there is a traffic lanes for the cars, etc. So there can be a congestion in the traffic lanes for the car, but the bus lane is open for the buses, and so they never wait, and they can guarantee the exact same duration for every round of the bus. And you can find this exact same system, for instance, in commands in airplanes. Like there will be a place in the network for injecting, say, a command by the pilot. And whether the pilot uses that command or does not use that command, there is a reserved place in the network every period, like 50 milliseconds or something. So whatever the pilot does, within the equivalent of my 45 minutes, the command will be transmitted to where the command is acted. Now, you realize that in a large city, you cannot have a bus lane from any point to any point. And so what you do in a city usually is you have to switch bus somewhere. You arrange to minimize number of hops, but the capability to be deterministic is conserved, because on the first stop, having to wait a maximum of 15 minutes and having 30 minutes of travel can be repeated over the second hop. Same thing, you will at the switching place where you go from bus A to bus B, you still have a bounded time to wait, and then a bounded a fixed time to reach the next stop. So what you do traditionally in a bus is exactly what we do in a switching or routing deterministic network. We actually allow switching, and that's how we save huge amount of cables. But at the same time, we manage to still guarantee the end-to-end deterministic latency. And with this, we can actually provide the emulation of a serial cable, which is of a point-to-point end-to-end serial cable, which is what we intend to replace with those deterministic networking. And by doing that, like I said, we save a lot of cables. The other analogy that I really like, and I guess it speaks to people, is the train analogy. So what you have here is the schedule of a train. Actually, I guess it's English. And what you see from those lines from top left to bottom right is actually a train going from station to station to station. So what you want to ensure, and the thing you're really after, is congestion loss. You want to avoid congestion loss. And guess what? Congestion loss means in this case that two trains go out of the same station at the same time on the same rail. And guess what happens, right? Congestion loss is kind of bad news. The way to avoid congestion loss is scheduling. What you see here is the trains are scheduled, so there is only at most one train outgoing the station on a particular rail. And I've enlarged a little piece of this drawing here, and what you can see is the blue train is actually waiting at the station to let a faster train go through without collision loss. And the end result is, if you look at it, that the blue train will take more time through the network than if it was trying to speed as much as possible. And you realize the trade-off, which is that probably you will have a higher latency for my blue train, but you will not have congestion loss, and you will have a guaranteed time of arrival. So determinism in a network often comes at the expense of the best possible latency. There can be one flow that really you design for, which will just go straight through my picture, but for most flows you will have some latency, which will be more than the average latency of hot potato. So the hot potato latency will look like a curve, like not a Gaussian, but some round curve. The deterministic networking flow will be more like a perfect line. Every packet will be delivered with the exact or very close latency, as opposed to the long tail that you can observe on statistical multiplexing. And that actually is the introduction to my last analogy. And this last analogy is that of casino. And what I mean by that is that in a casino, there can always be somebody who wins and wins and wins and wins. And obviously the chances that this happens are going down, 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 but they're never fully eliminated. And so what we intend to do in a deterministic network is to guarantee that for each packet there is this bounded latency. There is never a winner at the casino that will win and win and win over and over. So we are eliminating this rare but statistically plausible case of the packet being very, very light in the network. To summarize all this, deterministic networking is about providing some guarantees like loss and latency, bounded loss and bounded latency, and typically, not necessarily, but typically the way this is achieved is by scheduling the network to ensure that the amount of resources that are used in the network are perfectly controlled. So you have exactly the right buffers at the right time which are available for a packet, so the packet is never lost. And the queue for transmission is never filled. And you can always send the packet that you have to send, which is on a deterministic flow, at the time you need to send it. As it goes, one thing we don't want to do is build a network that would be dedicated to deterministic flow. So the other thing that we care to achieve is sharing the physical resources with best effort.